till now we have looked at the one-dimensional finite element problem using linear basis functions. So if we had this domain, what we had done is we had partitioned the domain into elements, we had corresponding nodes, and then for the element we went ahead and constructed approximations using these functions phi I, which are linear. Obviously the question is that all we can do, or can we do more than taking such linear approximations? The answer is yes. So what today we are going to look at is higher order approximations for the finite element solution. So what, as a notation, let us first introduce, when we say linear approximations, then we will represented by p equal to 1, where p we call as the order of approximation. Order of approximation. Now what we have implicitly assumed, and we will assume it throughout this course unless we specify specifically, that this order of approximation is the same in all the elements. That is, throughout the domain we are going to use the same order of approximation. One can always use different orders of approximations in different regions of the domain. That case we will not handle now. So let us now see how this order of approximation can be increased. So the next example that we will do is p equal to 2, that is, the order of approximation is quadratic. Okay. For this, let us see what is it that we have to do as far as the approximation is concerned. So for this, we take the same domain that we had taken earlier, okay, with an end load p. This is x equal to L, this is x equal to 0, and some distributed forces Fx. F of x. With, let us also take Ea is equal to constant in the domain. That need not be true. So using this, given this data for the problem, let us now go ahead and do the approximation. So how are we going to do this? What we need to do now is to first break the domain into elements, as we have been doing till now. Maybe I will take 4 elements here. So these partitions that I have drawn using these end vertical lines, these are our elements. So this is element 1, this is element 2, this is element 3, and this is element 4. Now in this element, in each of these elements, what I am going to do is add an extra point. So in each of the elements, I am going to add an extra point, which is, this point is located at the center of the element. Okay. So now we are going to give the locations of these points. So now instead of having 1, 2, 3, 4, 5 points for the 4 elements that we have drawn, now we have 9 points. So we will give them names. So this is point x1, this is point x2, this is point x3, x4, x5, x6, x7, x8, x9. What you should note is that these extremities of the elements are given by the point x1, x3. So these are the extremities of element 1. Extremities of element 2 are the point x3 and x5. Extremities of element 3 are the point x5 and x7. Extremities of element 4 are the point x7 and x9. These points x2, x4, x6, x8 are generally called mid-side nodes or mid-edge nodes. Okay. So we'll give a name to them. These are mid-side nodes. Okay. And the points x1, x3, x5, x7, x9 are called the end vertices or simply the extremities of the elements. So these points become end nodes. Okay, or element nodes or extremities of the elements. Okay. Now what do we do next? So what we will do is, over this point set that we have created, we are going to use it somehow to create our basis functions, which are quadratic in nature. So I have this point set. Then I am going to construct the basis functions which now should be quadratic in the elements. So first I am going to draw, then we will talk about how to construct them mathematically. So drawing wise, what had we said about the linear functions? What we wanted these functions to do was to have a value 1 at one of the nodes and 0 at all other nodes. The same principle we are going to use as far as construction of the quadratic functions is concerned. So let us take the function phi1, that is corresponding to the node x1 or the point x1. So phi1 will be 1 at the point x1 and 0 at all other points. So if I want to make that, phi1 is this function. Okay. Similarly, I would like to make phi2. Phi2 will be a function which is 1 at this point, at the point x2, and 0 at all other points. So, and what we see is that we have defined it in a local region. That is, phi2 is only defined in the first element. Okay. So, if I can draw that element here, this is element I1, this is element I2, this is element I3, and this is element I4. Then I can draw phi3 accordingly. Phi3 should be 1 at this point and 0 everywhere else. So, by the same token that I have done, phi3 is like this. Then phi4. Phi4 should be 1 here, 0 at all other points, phi4. Similarly, phi5 will be 1 here, 0 everywhere else. Okay. Similarly, if I want to use phi6 will be this, phi7 will be this, phi8 will be this, and phi 9 will be this. So what we got is phi 2 is here, so naming wise. This is phi 3, this is my phi 4, this is my phi 5, phi, sorry, I made a mistake here, so I have to go back and change my naming convention. So this was phi 2, this is going to be phi 3, this one is going to be phi 4, this one is phi 5, this one is phi 6, phi 7, phi 8, and then phi 9. So here I have the 9 phi's which I have constructed. They look quadratic. We have to also give an expression to them mathematically. Why are they quadratic? Because they have a value 1 at one point and 0 at two other points, and then we extend it as 0 everywhere else. So they should be quadratic, at least they look like that. Now in terms of these functions, how am I going to write my finite element solution? So UFE of x, we will use our earlier notation, is it is going to be U, it's a 9-term solution, U9 of x, this is equal to sigma I is equal to 1 to 9 Ui phi I. So this is a pictographical thing. Now what is it that these functions have to satisfy in order to be admissible basis functions? The first thing that we have done till now is that these functions phi i's should be linearly independent. Second thing that they have to satisfy is that they should be complete. And third thing that we have done by construction is they should have a local support. That is, they are only defined in one or two elements, and in the rest of the elements they are 0. So by construction we see that this property is satisfied. Linear independence we don't know, this we don't know. So let us first make these functions in such a way that they are quadratic, linearly independent and complete. So how are we going to do that? So to do that, let us now construct these functions element by element. So if I look at element, a generic element I k. If you look at the generic element I k, what are the nodes that this element has, or the points? It will be x 2k minus 1, x 2k, x 2k plus 1. Similarly, which are the phi's which are non-zero here? The phi's which are non-zero here are phi 2k minus 1, phi 2k, phi 2k plus 1. So let us now go and transform this to our element notations that we had introduced earlier. So from our element notation point of view, in the element, I will call this first node as x1 of element k, the second one x2 of element k, and the third one is x3 of element k. Similarly, the phi 2k minus 1 in this element would be called n1 of element k, and phi 2k will be called n2 of k. Similarly, phi 2k plus 1 will be called n3 of k. And like in the case of linear approximations, in this case we want these functions n1 of k to have a value 1 at the point x1 of k and 0 at all other points. n2 of k should have a value 1 at the point x2 of k, 0 at all other points. n3 of k should have a value 1 at the point x3 k and 0 at all other points. So what we can write in short is Nik at the point xik is equal to 1, and at all other points j it is equal to 0. This property is what we want to have for this function. So if I want to construct n1k with this property such that n1k is 0 at the point x2k and x3k, so how will I form the function n1k? This should vanish at the point x2k. So certainly this representation should have this form, right? Something into this. So if something into this is there, then at x2k this expression goes to 0. It should also vanish at the point x3k. So it should also have this part sitting there. So you see that this expression vanishes at the point 2 and the point 3 of the element. Now what else is required? At the point 1, this expression should have a value 1. So what I will do is simply divide by what I have done in the bottom part, I have replaced x with x1k. You see what has happened. This is a quadratic expression. It vanishes at the point where we want it to vanish, and it has a value 1 at the point where we want it to have a value 1. So, by the same token, can we define n2k? Remember, we are defining these things only in the element ik. This will be equal to what? Very simple. It will be x minus, it should vanish at the point 1 and 2, so it will be x minus x1k, x minus not 1 and 2 but 1 and 3, x3k, and it should have a value 1 at the point x2k, so it will be x2k minus x1k, x2k minus x3k. Similarly, n3k by the same token can be written as x minus x1k into x minus x2k divided by x3k minus x1k into x3k minus x2k. So we have constructed the 3 functions at the element level which satisfy the 3 requirements we have imposed as far as the values are concerned. Okay. Now, what do we know? That if I look at the function phi two k minus 1 of x, where is this function? And this is for, we have to differentiate between the 2 things. This function 2k minus 1 corresponds to an edge vertex, that is a node which is shared by 2 elements. That is, this corresponds to, if k is 1, it is 1, so it is 1, 3, 5, 7, 9. This function has to be non-zero in the 2 elements sharing that node. So, this will be equal to n3 in the element k minus 1. For it will be n1 in element k, and it will be 0 everywhere else. So what we have said is, this function, if I talk of this node 2k minus 1, this is element ik minus 1, this is element ik. Okay. So this, the function is given as n3 of k minus 1, which we now know how to construct, and here n1 in k. So this way we can construct all the global basis functions, odd ones, using these nik's defined in the element. What about the phi 2k, that is the even ones? The even ones, if you see, are defined only in the element. So the even ones, the phi 2k, k is equal to 1 to the number of elements. These are sometimes called internal bubble functions. And they are only defined over element ik. That is, this is my element ik, so this is my the 2kth node, and phi 2k is non-zero in this element and 0 everywhere else. So what we know now, that phi 2k is equal to, by definition, n 2 of element k in element ik and 0 everywhere else. Okay. So these, now you see that when we came from the linear to the quadratic, the construction has become a little involved. Nevertheless, the steps that we are going to follow will be the same, irrespective of whether it is linear, quadratic, and as we will see, cubic, fourth order or fifth order, any order that you would like to have. Now the question is that, are these functions linearly independent? So once I have defined these functions Ci, then if you remember, we had written u9 of x is equal to sigma I is equal to 1 to 9 ui phi I of x. How do we check linear independence? If you remember, linear independence means that if this function is identically equal to 0, then the coefficients ui should come out to be equal to 0. How do I show that the coefficients ui are 0? So for that, let us see a very important property of these functions. What are these phi i's? If you remember, these phi i's have a value 1 at the node with respect to, or the point with respect to which they have been defined, and at all other points that we have put in the domain, these functions are 0. So if this function u9 of x has to be 0 everywhere, it has to be 0 at the point xi also is also equal to 0, which is equal to, from the summation, what do we get? All other phi's will vanish there, only the ui will remain. This will be equal to ui. So if I do this for all the 9 nodes we have in the domain, what do I get? That from this condition, that u9 is equal to 0 everywhere, we get that all the coefficients ui are 0, which means that the phi's are, these will be called piecewise quadratic, that is, in every element they are quadratic and linearly independent. What about completeness? So for the completeness, if we go and what do we want to do? We would like to see whether a function of this type, if the function is f of x, this function is given as a generic quadratic a0 plus a1x plus a2x squared. If I have this function, then I should be able to represent it as a linear combinations of a phi i's. That is, I will call it as alpha I phi I. Now what is this? Because we are saying these approximating functions are piecewise quadratic, for completeness we want the series represented by these functions to exactly represent at least a quadratic polynomial, not more than that. So either I have, if you see these are arbitrary coefficients. So this series has to exactly represent the constant represented by the a0, or a linear which is a0 plus a1x, or a quadratic which is a0 plus a1x plus a2x squared. So if it has to do it in the whole domain, then it should also be able to represent a quadratic in an element. So in the element, if I write, so instead of doing it in the whole domain, let us do it in the element. So in the element, if I want to write fx, it is equal to, I will call it alpha 1 of k, n1 of k plus alpha 2 of k, n2 of k plus alpha 3 of k, n3 of k. And this, let's say that the quadratic polynomial that we have taken, in the element it is of this form, beta 0 plus beta 1x plus beta 2 x squared. Now, by the way these functions have been defined, what will the alpha 1 of k be? Alpha 1 of k will be equal to f evaluated at the point x1 of k. Alpha 2 of k will be equal to f evaluated at the point x2 of k. Alpha 3 of element k will be equal to f evaluated at the point x3 of k. So, with this representation for the alphas, one should go and check that indeed what we had done in the previous page is really, I do not know whether this is going to be like this. So, this equality is a question mark, and what we can now check is that this is not a question mark, but indeed this is an equality. This is a simple algebraic exercise, and one can show that yes, indeed this linear combination of these three functions is able to exactly reproduce a quadratic polynomial defined in the element and thus in the whole domain, which means that this function phi I, the set of functions phi I represent a complete set. So, this in the construction of this phi i's, one has to be very careful. One cannot arbitrarily define this function phi I as we wish. Now, you see this point x, another point I have to note is that the point x2 of k that we have taken, point x2 of k, we have said it is at the mid side. It need not be, it could be anywhere, but as a convention, it is taken at the middle of the element, always. But one should remember, it need not be the case, especially when we have curved elements, which we will be dealing with later on. Okay. So, now that we have defined the phi i's, what next? So, once we have defined the phi i's, the next thing that we have to do is to go ahead and find the coefficients ui in order to form the solution to the problem. Okay. So, to form the coefficients, where do we start from? We start from the weak formulation. And for the problem that we have taken, the weak form is very easy. So, it is x is equal to 0 to L. It will be Ea du dx fv dx plus c into v evaluated at L. Now, in this weak form, what do? We go and substitute instead of u9. So, this will be replaced by u9, and to form the ith equation, what do? We replace v with Ci. So, to make the notations a little bit compact, this part, as we had done a few lectures ago, we are going to represent as a bilinear form. As I had said, it is linear in u and v. So, it will be called as the bilinear form given by this compact notation v u v. And this side, this we are going to call by f of v, which is a linear functional and given by the name f of v. Because here, as the number of functions increase, the algebra gets tedious, so we would like to be compact. Only for that reason we are introducing these things. Okay. So, the ith equation is given as b of u9 Ci is equal to f of Ci. Okay. So, now if I have this, now I can expand the u9. So, what will that be equal to? I can write it as b of sigma I is equal to 1 to 9 ui sorry, not I, we will call it j, uj, comma phi I is equal to f of phi I. Now, since this is bilinear, by the definition of a bilinear function, this summation over this coefficient I can take out. So, this is equivalent to writing sum of j equal to 1 to 9 b of phi j phi I whole thing multiplied by uj is equal to f of phi I. Okay. If you see for the ith equation, this term becomes the coefficient of the jth unknown. So, what is it called? If you want to go back to what we had done earlier, this term will be equal to k for the ith equation jth column. So, this is Kij. Now, our job is, so if this is Kij, then we can write the whole problem in the form of the global stiffness matrix K into the unknown displacement vector U, where now this is K is 9 by 9. U is a vector of size 9, this is equal to the vector F. Okay. So, our job is to find the entries of this matrix and of this vector. So, if we can find these entries, then we have assembled the matrix problem, and all that we have to do is invert this matrix. First, we have to apply boundary conditions, invert the matrix, and the solution is there. Okay. So, to do this, what do? We have to again go back to the element calculations. So, element level calculation. Now, let me redraw the whole figure again for the element. This is x1 of element k, x2 of element k, x3 of element k, and if you remember, so this was n1, n2, n3. So, this was n1 of element k, which is equivalent to phi 2k minus 1. This guy is n2 of element k, which is equivalent to phi 2k, and this one is n3 of element k, which is equivalent to phi 2k plus 1 in the element k. Okay? And just like we had done for the linear problem for the p equal to 1 approximation, here what do we note? That the phi's which are non-zero in the element are these three phi's, phi 2k minus 1, phi 2k and phi 2k plus 1 for k equal to 1, 2, 3, 4. That is the number of up to the number of elements. Okay? So, what the element is going to contribute to is the 2k minus 1th equation, 2kth equation and 2k plus 1th equation. And which rows of these equations are going to be non-zero? Which columns of these rows are going to be non-zero? The columns which are going to be non-zero for each of these rows are the 2k minus 1, 2k and 2k plus 1. To these columns only the element is going to contribute. To none of the other columns it is going to contribute. So, if I take that B that I had written, phi j phi I, which is nothing but, as we had said, Kij, which of the i's and which of the j's will get contribution from the element? So, as we have said, I equal to 2k minus 1, I equal to 2k and I equal to 2k plus 1. Similarly, j is equal to 2k minus 1, j equal to 2k, and j is equal to 2k plus 1. So let us find these contributions. How had we found these contributions earlier? So what we are going to define now is for this element k, the element stiffness matrix. Now what will be the size of this element stiffness matrix? Because there are now 3 n's or 3 phi's which are non-zero in the element, so it will be a 3 by 3 matrix. Okay. So what will the entries be? I will write only a few entries of this, and then so it will be integral from x1k to x3k EA d n1k dx d n1k dx. This I will take. So for the first row of this, I will have EA d n1k dx into d n1k dx will be the first column entry, EA d n1k dx into d n2k dx as the second column entry, and the third will be d n1k dx into d n3k dx as the third column entry. And similarly, if I come here to the second row, so it will be x3k EA d n2k dx d n1k dx and so on. And the third will have integral x1k to x3k. You see the limits of the integration are from one extremity of the element to the next extremity of the element. So that should be kept in mind. D n3k dx d n1k dx. Okay. So can I write the kij in the element k? This will be equal to integral x1 of k to x3 of k of EA d njk dx d nik dx. Similarly, fi in the element k will be equal to nothing but x1 of k to x3 of k f nik dx. Remember that here we are not going to add the part due to the p. That is going to be added when we are applying the Neumann or the force boundary condition. So this is all that the fik from the element will have. Okay. So once we have this, then we have obtained the element level stiffness matrix and the element level load vector. So this will go to the element load vector. Okay. So once I have these, now what do? We have to find the correspondence between these element level entries and the global entries, that is, where in the global stiffness matrix should this Kij go. Globally, it is which Mn it should go to. Okay, that is where I have to assemble this thing. Similarly, where will the Fi at the element go to globally? Which F n. This equation, this information we have to have. So what had we done earlier as far as this information is concerned? We had created a local to global numbering. or many times it is called the connectivity information. Okay. So this connectivity information has to be constructed. So let us now do it for the element. So what I will do is, here I write the global number and here I will write the corresponding local number for the element k. So this is the local number 1. In the element I have how many? 1, 2, 3. Which global number does it correspond to? 1 corresponds to which global basis function? N1k corresponds to phi 2k minus 1. So it should correspond to, globally I will rewrite it in another form, 2k minus 1 plus 1, which is nothing but 2k minus 1. This one will be N2 corresponds to phi 2k globally. So it will be, I will rewrite it as this, plus 2. Similarly, N3k will correspond to phi 2k plus 1. Okay. So remember what we have done. So before we go and do the element calculations, we have set the entries of the global stiffness matrix and the global load vector equal to 0. The process of assembly that we had talked about in great detail in the previous lectures essentially is adding the elemental contributions to this global stiffness matrix and the global load vector in order to complete the global equations. Because what we had said is this integration over the full domain can be partitioned into the integrations over the elements. And when we add these elemental integrals together, we get the global representation. So the global entry which is going to get contributions from the elements are going to be k 2k minus 1 plus I comma 2k minus 1 plus j is equal to, what we are going to do it is to the original number which was sitting there, I am going to add kij. So what has happened? To the global stiffness entry k2k minus 1 plus I, 2k minus 1 plus j, I am going to add the elemental ijth entry. So this is the part, the assembly part as far as the stiffness is concerned, and this is for I comma j is equal to 1, 2, 3. Similarly, the f 2k minus 1 plus I will be equal to f 2k minus 1 plus I. To this I am going to add f k I. So this is the assembly procedure. Okay. So we have obtained the element calculations using the functions which we have defined at the elemental level and assembled them to get the global equations in terms of the basis functions that we are after, the coefficients for the global basis functions. So one should remember that in any finite element approximation, we are really looking for the coefficients of the global basis function, and the element calculations are a simple way of doing the integrations, relevant integrations that have to be done to obtain the entries of the global stiffness matrix and the global load vector by doing it at the element level, adding it up to get the global equation. One question that should come to mind now is, earlier we had seen for c equal to 1 that the ith equation had only non-zero entries corresponding to the I minus 1th column, the ith column and the I plus 1th column. In this case, what are the non-zero entries for the ith row? So let us take, I will not take the ith row, I will take this one as the 2k minus 1th point. Okay, so this is 2k minus 3. So here we have to differentiate between these nodal functions and the internal bubble functions. So let us take the nodal functions that we have. Okay, so if you see that I am talking of the equation corresponding to this one. So I am corresponding to the equation corresponding to this function, which is phi 2k minus 1. Which of the phi's are going to contribute to the equation corresponding to this? Certainly it is going to be this phi. Certainly it is going to be this phi. It is going to be this phi and this phi. So this is going to be phi 2k minus 3. This is phi 2k minus 2. This is phi 2k and this is phi 2k plus 1. So what can you see? That for the 2k minus 1th equation, okay, so 2k minus 1 equation will have non-zero entries corresponding to the 2k minus 3 column, 2k minus 2 column, 2k minus 1 column, 2k column and 2k plus 1 column. So how many columns will be non-zero? 1, 2, 3, 4, 5. So 5 columns will have at least, not at least, at most 5 columns will have non-zero entries. Okay. For all other phi's, the column entries are going to be 0 because all other phi's are going to disappear or become 0 in the region where the phi 2k minus 1 is defined to be non-zero. Okay. So you see that if I write the global stiffness matrix, the number of non-zero entries has increased in a row. Okay. This is another property of these approximations that we are going to see and how they reflect in terms of the sparsity of the global stiffness matrix, and that also, even the sparsity we are talking about, we have to talk about solvers. So this we will tackle at a later date. Okay. See, there is a very curious thing about these functions phi k. These functions phi k, if you add them up anywhere, you will see their value is equal to 1. Why is it so? Remember, we had said that these functions phi k should be able to exactly represent any polynomial up to a quadratic. So a constant is also a global polynomial which should be represented exactly, and in constant I will take my function fx which I want to represent to be 1. This will be equal to sigma ui phi I. Now if this function is equal to 1 everywhere in the domain, it has to be 1 at the point x1, x2, x3, x9. So if I go to the point xi, this is still equal to 1, but then this will be equal to ui. Okay, which tells me that the ui's here on the right hand side are all equal to 1. If the ui's are all 1, then what we get is sum of the ci's is equal to 1. And this is also true in the element. Same thing applies in the element. So in the element, sum of the shape functions will be I is equal to 1 to 3 is equal to 1. This is a property that we should keep in mind, and what it also tells is that it implies that if I do this summation, this has to be equal to 0, because this sum was equal to a constant, the derivative of a constant is 0. These are certain things which we should have in mind, so that when we go and write the computer program to do the finite element analysis, we can check our functions, these basis functions or the element shape functions that we have called, which are ni's are nothing but the element shape functions. Okay, we can check whether they have been correctly programmed or not. The definition of these element shape functions that we have used, this definition is called Lagrangian shape or basis functions. Okay, we will see how to generalize these to go for a kth order approximation in future. Okay, so these Lagrangian basis functions that we have constructed are not the only ones that we can have. For those who are interested, there is also a very popular family of shape functions that or basis functions that can be used is Legendre functions, but we are not going to discuss it here in this analysis. Okay. In the next class, what we are going to do is we are going to look at the cubic approximations, the p equal to 3 approximation, how to construct these basis functions, how to do the elemental calculations, how to go for the load vector, and from there we will generalize to the pth order approximations. And once we have done the pth order approximations, then we can do a finite element computation using any order of approximation in the domain. After that, we will see how they are going to benefit us. Just doing them is not enough. Why we should do them, how they are going to benefit us, is going to be in the future lectures. Thank you.